Hi, we're Group 7, and our project is on aircraft loading optimization. So loading an aircraft is a simple task in first glance because we just want the torques to remain balanced. But from an airline's point of view, it's actually quite a complex coupling system because we want to find out what's the maximum profit by carrying passengers or cargo, but we also need to figure out how to put them in cabins, containers, and where to put them on the airplane to remain balanced. So that calls for a system optimization of three subsystems. And in our case, we're studying a ANA flight from Los Angeles to Tokyo with a given flight and configuration. So here's a system flow diagram showing our three subsystems with their respective inputs, outputs, and coupling parameters, which we'll go in detail in the following slides. So for the profit subsystem, our job is to figure out what's the maximum profit given certain constraints, and finally give out suggestions on what's the suggested passenger count on each class and whether to take a cargo or not, and also make initial guesses on container and pallet counts. So for definition of constraints, passenger count, container, and pallet count should all be integers, and they have their respective upper-lower bound. And we have 4 constraints here. As for the definition of objective function, we have fixed ticket prices and a list of end cargo items from the logistics teams with random weights and shipping rates. And our job is to maximize the revenue by adding up ticket fare and the chosen cargo's value. So the trade-off here is that you'll see that the theoretical maximum is 10,000, which is larger than any of the ticket prices. So cargo should be replacing some passengers. So modeling approach, we took analytical and we made some additional assumptions, plugging them into the constraints we had earlier, and this is what we get. For optimization method, we chose MATLAB's integer linear programming because our model has no nonlinear terms and all of our design variables are integers. So for our optimization results, here is what we get under default settings. So what this is telling us is that with a given cargo list, selling more than 176 $600 economy seats is not profitable. So if you're selling C numbers higher than this, you should charge more than 600. We also played around with space limit and weight limit, and we found that our problem is mainly weight constraint. We also changed our economy ticket prices and made our candidate list of cargo longer, which basically raises the mean value of these cargos. And we found out that these changes can be explained because our problem is weight constraint. So revenue per kilogram is actually key. So if we do a quick calculation, we'll see that for business and premium, they beat economy and cargo by a lot in terms of US dollar per kilogram. That's why they always get filled up in all cases. And then for the subsequent cases, it's basically a battle between economy and cargo.
Logistics subsystem has 2 integer design variables, number of AMF containers and PMC pallets. Each passenger weighs 136 kilograms, including carry-on and check bags. A cargo list has 150 items across 15 categories, with weights from 5 to 1,000 kilograms and rates of $3 to $10 per kilogram. The 7879 provides 18 cargo stations, split into 10 forward and 8 aft. The key constraints are the containers and pallets, which need to be less than or equal to 18, and the 53,000 kilogram weight limit covering passengers, cargo, and deadweights. An objective function minimizes labor hours based on the coefficients shown on the slide. These coefficients come from worker minute calculations for container buildup, pallet buildup, and a fixed overhead. The main trade-off is that more pallets increase cargo revenue, but also add about 2.92 labor hours each. We use an analytical approach for the labor model and greedy knapsack heuristic to select cargo based on profit per kg. The process has 5 steps. First, take the linking variables from the profit subsystem. Second, generate the cargo list using the shared seed. Third, compute the bag weight using partial container logic. Fourth, assign bags and cargo to the forward and aft compartments. And fifth, calculate both labor hours and critical path turnaround time. The list slide shows how each labor coefficient was calculated within the bottle. The right side shows the weight budget. With 228 passengers at 136 kilograms each, the passenger weight is nearly 31,000 kilograms. The total non-cargo weight is about 33,000 kilograms, leaving only close to 20,000 kg for cargo based on 53,000 kg limit. Since the pallet capacity is 35,700 kilograms, only 56.2% of this can be used, confirming that our system is weight limited.
We enumerate all feasible integral combinations of A and P in MATLAB, filters and hybrid points, so no iterative solver is needed. Cargo selection uses a greedy heuristic ranked by dollar per kilogram, which matches the profit subsystem's integral linear program solution exactly. Swiping P from 0 to 7 with A fixed at 4, pallet capacity bands below P equals 5, and the weight limit bands above. At the profit solution P equals 7, we load about 20,000 kilograms of cargo at about 23 labor hours, but the pallets are only 56% utilized. The greedy heuristic matches a linear program at all tested pallet counts. Beyond P equals 5, labor keeps growing, but cargo is saturated at the weight limit. Cargo averages $6.5 per kilogram versus economy at 4.41, which is the why profit subsystem displays economy seats for cargo. The 787-9 is weight constraint, not volume constraint. Logistic is a unidirectional follower receiving input from the profit subsystem. At the system level, the label penalty will treat cargo revenue for efficiency with the weight budget as a bending shared constraint.
For the mechanical system, we developed an optimization model to determine how passengers and cargo should be distributed in the aircraft to maintain a balanced center of gravity. Starting with the inputs, the model uses arm locations for passengers and cargo and passenger counts from the profit subsystem. Each passenger is assumed to have a total weight, and the cargo is categorized into containers and pallets with known weights and special requirements. The design variables include how passengers and cargo units are placed. Next, we compute intermediate quantities such as the index contributions from passengers and cargo and the forward and aft cargo weights. The objective is to minimize the deviation of the total CG index, which is formulated as minimizing the square of the total index. The model is subject to several constraints like passenger counts must match the required totals, cargo stations cannot overlap, pallets must occupy consecutive stations, forward and aft cargo weights are limited, and all cargo must remain within allowable bounds. For modeling, this is a discrete optimization problem where the passengers are allocated to rows and cargo assigned to stations. We assume that containers occupy a single station while pallets occupy two consecutive stations. The CG index is calculated using momentum principles where each weight contributes based on its distance from the reference point.
The mechanical subsystem is optimized by the genetic algorithm implemented in MATLAB. The reason for this is it works well with nonlinear constraints and our nonlinear objective function, and it's suitable for our discrete loading and placement problem. Because our discrete design space is small, we don't see issues involving the time it takes to run the algorithm. Additional schemes we implement include forward and aft compartment allocation for the CG check, floor rounding to enforce discrete station assignments, and constraints which prevent station overlap. Our optimization produces the number of passengers allocated across each row and optimal container and pallet locations in the cargo bay. For our objective value, it does vary each run, but we average around 127. We see this being somewhat large due to the discrete nature of our problem. We still meet all our constraints, including passenger seat totals, cargo station assignments not overlapping, forward and aft weight limits, and our final CG index being within upper and lower bounds, indicating the aircraft can still fly. Here are some results from test cases we have run. Because the profit subsystem has found that the business and premium economy cabins are essentially full, we see that pallets are generally placed in the back of our aircraft to counteract the movement from the fixed business and premium economy cabins. Overall, our optimization finds a feasible loading that maintains CG balance within all operational constraints. Cargo placement significantly affects aircraft balance, and an even weight distribution is pushed by the optimizer. In terms of coupling, profit and logistics have direct inputs into our subsystem, and mechanical outputs a CG index, which, if too high or too low, can reject profitable mixes. Overall, the mechanical subsystem acts as the final safety gate, ensuring aircraft stability before dispatch.